I'd like to thank the organizers for allowing us to come and present at this SPE IADC meeting here in London. Today we're going to be talking about drilling modeling and simulation, current state, and some of the future goals. And on this team who's put together this review paper, we've had Junichi, who's really led the development and organizing this paper, Robello from Halliburton, and Joachim from Baker Hughes. We have George Ostermeyer, Braunschweig Technical University, myself, John Hedengren, and Paul Pastusik from ExxonMobil. You can see from this list it represents members from service companies, major operators, and universities. And the collective experience of this group in this area is great. There's worked many of them entire careers in this area. So we want to provide some perspective on the current state and future goals for modeling and simulation, and some of the things that are important for those who are listening to this. There may be key decision makers wanting to quantify benefit for the organization, whether they invest in modeling and simulation. There may be those who use simulators wondering about the new developments coming and what is current state of the art. And there also may be developers who are developing these simulations and for industry, and what are the challenges and opportunities? What should we be working on right now? Where's the biggest benefit that's lying there? So I want to try to answer these today and review a number of outline of future challenges and opportunities in this area. So let me just begin by just giving a perspective on some of the computing and data capabilities that we have now. In the last 15 years, so since year 2000, computers have increased in speed by 1,000 times. Okay, that's just for computers. And then also, if you look at standard benchmarks for optimization algorithms, those have also improved by 1,000 times. Okay, so what we have then is we can solve these same optimization algorithms 1,000,000 times faster than we could just 15 years ago. And so what's the opportunity there? How are we using that to be able to deliver value for drilling? Let's also consider the rate of data transfer to downhole equipment. Now, this is just a logarithmic scale on data transmission rates. And you can see mud pulse technology has been one of the main methods of communication. But that's been limited to fairly low bandwidth speeds, certainly below 100 kilobits per second. So with adoption of wired pipe technology, there's been a step change as well in the data transmission rates, both bidirectional, to downhole equipment, and also up from instruments. But also the rate has improved dramatically. So we combine this with computers and algorithms, and then also with data, and there's a significant opportunity here to do something with this data and the algorithms. So let's talk a little bit today about how we exploit some of that and to improve the drilling process. Okay, so here we have various simulators, and I just want to, again, big picture view. This is our world. There's a certain region. We draw a box around a certain region and have some limiting assumptions. But this becomes our system, where we have some input data and then also output data, and we're trying to be able to determine if we have changes in the input data, how does this output change? Now, there's different ways that we've done that. Here is maybe an operator, and he sees, from training simulators or practical experience, he's seen a number of input data and output data okay, with various consequences. And so he correlates in his mind through this neural network a relationship between the input data and the output data. And human brain is very good at doing this. So we also have, for example, physical models. Let me change that to a data. We have physical models, and so those we create a physical representation, maybe scaled down, of the actual system, and then we give it the same input and output data. So this would be a hardware model. We also have virtual models, for simulation, where we try to give it the same numerical values of the input and to see if we can predict similar outputs to what was observed in the real system. And we may also have a combined, or hardware in the loop or software in the loop system, where we combine this input data, and we have parts of it that might be represented by a physical model, parts of it that might be represented by a virtual model, and then parts of it that can sense or actuate, provide additional data for these two models, and then produce the output. So there's a variety of range of simulators that we can use to be able to approximate or understand our world. Okay, so let's talk about the drilling process. So there's topside equipment, there's drill pipe that we're concerned about, there's hydraulics, the flow of fluid down through the drill string and then out through the borehole. And then we also have rotation that we're concerned about, the formation, what we're drilling into, hole cleaning. So, can we drill faster, and what is stopping us from doing that? It might be, too high of concentration of the cuttings. Shock and vibration, human factors are important in modeling, and then saccadic, it's inherently stop and go. So we, so that's another challenge in the drilling. There's also discrete phases of operation, all leading to challenges for modeling the drilling process. Okay, so let's talk about a little bit about drill string dynamics. So they're a major cause of bit and bottom hole assembly damage and reduced drilling performance. So one particular company reported in 2012 that shock and vibration accounted for hundreds of millions of dollars, or a quarter of their total loss. So this is a big area to work on. We want to be able to develop, in the 80s, researchers developed finite element-based dynamics, and recent progress has been in nonlinear development, hydraulic effects, thermal effects, arbitrary buckling and snaking. And then we've also had recent work in soft versus stiff string assumptions. Soft string being no interactions with the borehole when it's considered to be vertical, and then stiff string is when there is interaction with the borehole, and so you have it's typically in horizontal sections. So data on drill string dynamics has also been reported, 500 kilobits per second for wired drill pipe, and 1400 hertz while data logging. So a lot of data to be able to detect high frequency vibration and other effects to validate the model. So coupled items of future work, coupled vibration models, vibration with lab and rig data, predictions of damage due to severe vibration, whirl, and bumpy bends. Let's talk a little bit more about hardware in the loop drilling simulators. This is the Cella process where they've made this distinction, or this cut between the top side borehole and then the bottom hole assembly area. And so with this, we've modeled the Cella process with the computer, okay, and then also created an interface to this test rig that models the with a physical model the bottom hole assembly. So this is a procedure for simulating at time t. Let's just say time, start of time. We have this complex geometry by forces at the interface. So just giving it initial conditions, but also this complex geometry. We first of all, simulate and at the boundary, what needs to take place, and then we give those inputs to the boundary of the physical model. We measure the forces then that result from the input-output relationship of the physical model, and then feed back that information back to the simulation model. And then step to the next time. So we just increment by a certain amount of time, and then return to the simulation model, go down to the physical model again, and create essentially a loop here where there's a distinction between the software and the hardware. But we have this hardware in the loop simulator, and one of the reasons why we might want to do this is if this would be too difficult to obtain with software, or maybe not realistic enough, or maybe there's certain vibration frequencies that are too high resolution, or there's a variety of reasons why we might want to do this. But the hardware in the loop, you can split these in different ways to have essentially replace certain parts of it with software or hardware. Okay, so let's talk about uncertainty, because this is important when considering the drill string, the drilling fluids, rock mechanics, etc. Okay, and then we combine that with these nonlinear stochastic partial differential equations. So very sophisticated equations, maybe finite element methods to discretize. But some of the things that we're concerned about are uncertain and nonlinear, maybe conditional and moving boundary conditions. We may also have spatially distributed systems, large energy stores. And so as we think about each of these things, it's like these three blind men exploring the elephant, and each one has kind of sees different things, aspects of this elephant, and so they're trying to put this together. And how do you do that? How do you couple these models with so much uncertainty about each of these individual elements? Okay, so you also have, for example, downhole measurement delays. How do you reconcile that? How do you if you don't have high-speed telemetry, how do you deal with time average data or other effects of measurement delays or slow data transfer? Also, you're controlled from the surface, but you're inherently trying to control things that are kilometers down this string. How that's just another challenge with uncertainty, control delays, actuation delays, and then you also oftentimes have limited downhole measurements, and also very little downhole control. Okay, so when we don't have a long string measurements as well, sometimes we're in the dark about what's actually happening. We have a mathematical model, but we may not have a complete understanding of what's actually happening. Okay, so let me go over a couple key observations. Now this is a perspective from an operator. Key observations are that drilling modeling solutions, they're provided by diverse groups, and so as an end user, there are many different options and backgrounds from these groups that you could potentially provide or acquire some of these models. So there's very high variability in the depth, breadth, and the quality of solutions coming from these diverse groups. So there's a lot of time spent trying to quantify the performance and perhaps benchmarks to be able to judge each of these different vendor solutions. Validation. Now this is seen as a common area of weakness. That how do you tell if the model has been validated? That was it validated with data? Was it validated with other simulators? What's the validation process, and is that documented? Benchmarking of products. This was identified as an area where more effort is needed. In the case of, for example, reservoir simulation, SPE has put together a number of benchmark reservoirs to which reservoir simulators can be judged, and so they all of the different vendors will simulate on these different reservoir simulation standards, and then this provides a benchmark to say, well, how consistent and how accurate are these simulators. Okay, so certification. Is this needed for drilling solutions, especially with liabilities in this area? Is certification needed for these drilling solutions? Model limitations and assumptions. Often these are not understood, and one of the reasons for this is that there are proprietary models, and sometimes the vendors are not willing to share some of the details, and also limitations and assumptions. If there's severe assumptions or limitations, sometimes those are they don't want to necessarily tell the full details because of marketing reasons, for example. Okay, integrated solutions. These are obviously preferred by operators, but it can be difficult sometimes to integrate different specialized software together into to fulfill an overall larger objective. Okay, you also have niche applications used that have technical edge. Okay, so very specific applications. And fit for purpose training. This can be challenging, especially with turnover in organizations, shifting roles and responsibilities. How do you train and get operators to a very high level on these training simulators or simulators? This can be a challenge. And then you also have technical specialists. These are going to be key to maintaining product efficacy. And you see in organizations that there are key individuals who need to fulfill that role of, this isn't just the software, it's software plus people that deliver solutions. Okay, so let's just talk about a couple future opportunities. Okay, so we've talked about some of the perspectives, where there are gaps from an operator's perspective. Software certification would certainly be one of them. It's something that's verified and validated. And let's just go over just a couple of these. This is a long list, so let me just go over a couple of these. You might have improved input safeguards. Okay, so data validation. How do you deal with data that might be sparse or corrupted, outliers, noise, drift? This is a common thing that we've heard from many operators, is that sometimes the data isn't good enough for some of these advanced techniques that we want to implement in real time, for example. And so the data quality needs to really be addressed. And this is a major focus for the DSATS committee, the automation committee within SPE that is taking a look at this particular thing with data quality. Okay, so let me go over just another one, independent benchmarking. We've talked a little bit about that. The SPE reservoir models. Does there need to be something similar to that for drill string dynamics or hydraulic models? Is there an independent benchmark that would give the same assumptions data and see how these different simulators perform? Okay, and then enhanced training. This is a big deal as well, to deepen the capability, to be able to use these simulators to the highest level of capability. Okay, so let's talk about just this drilling modeling and simulation discussion session. We had this at the ATCE meeting in Amsterdam, and many of the co-authors on this paper were on this panel. Some of the main points that were brought up from this is that there is a missing verification of results. That's a major shortcoming of the current simulation techniques. They produce results, but how do we know the confidence in those predictions? Okay, then we also have diversities of methods and a missing common industry approach in drilling modeling and simulation. Okay, we also want to define the model scope and complexity, and this is going to be very application dependent. There's going to be some finite element simulators, for example, that are going to be very good at describing bottom hole assembly performance, for example. This is a Schlumberger simulator right here. Bottom hole assembly. This might take a couple minutes to simulate that, nearly real time. But there might be simpler models that can be used for real-time application to dampen vibration, for example. And so it's really application dependent. So one of the other points that was brought up from this is that high-speed communication is really going to be a step forward in terms of verifying these models, and then also in automation. You can see that as the drill pipe are connected, that there's an inductive coupling that allows a continuation of this coaxial cable to downhole measurements, and also provides two-way communication. Okay, so this is going to be potentially a game-changing technology to provide data from models and maybe hardware-in-the-loop simulators as well. Also alleviate some of the uncertainties that have been plaguing these models, and then also accelerate advances for process automation and control. So let me go over a couple of the conclusions from this. That drilling modeling and simulation has become one of the driving factors for advancing this automation and control, intelligent managed pressure drilling, and then also drilling performance optimization. And some of the areas that we've been able to achieve and make really significant progress on in the last couple of years are, for example, in downhole dynamics, hydraulics modeling, and some of the topside equipment modeling as well. Okay, so this high-speed, two-way communication and a long string sensors, they're going to enable these models and simulators to be validated, and also that drilling automation systems are going to emerge that really utilize this intersection of increased computing, in improvements in algorithms, and then also improvements in data transmission rates. So we're going to see that we need to verify and validate these models, and that's going to be increasingly important as we use these for critical decision-making tasks. And then also, from the operator's perspective, the modeling assumptions and limitations need to be clearly communicated to the users. There's also a need for the integration of models. There's so many specialty or specific application models, but just like the elephant, we want to try to put those together into something that may have some benefit for these larger scope, where there's some cause and effect relationship between different models that can be exploited to deliver additional value. Okay, and then there's also a strong demand to find some industry common standards, which could help to ensure the quality of the results and strengthen the confidence with end users. Okay, so with that, I'd just like to acknowledge and thank the employers of each of these who have participated for permission to publish, and we'd also like to thank for the 2014 SP-ATC organizers for allowing the drilling, modeling, and simulation special session, and also encouraging the cross-industry academic collaboration on this topic. And of course, we'd like to thank the organizers of this SP-IADC drilling conference and exhibition, and for allowing us to come here and present.